Hello guys and welcome to another video. Today we're going to be talking about doing hand checks on core walls design. So we've got this simple core that is 2.7 meters in its shorter direction and 3.3 meters in its longer direction with 180 thick overall thickness throughout. We've got our design shear and overturning moment in the Y direction and in the X direction. So first, let's start by looking at calculating the tension and compression stresses and forces at the ends of either side of the core. First, before we jump into that, let's first look at our forces that is coming from the Y direction, and let's generally understand how is the force is going to flow over here. So if these forces are coming from the slab into the core wall, they will basically be pushing onto the core. So this shear force of 600 kilonewton is going to be resisted by the two strong axes of the wall, this one and this one. So these two are very stiff. Each of them is actually going to be resisting our 600 kilonewton. I mean half of it. So 300 is going to be resisted roughly by this one, and 300 is roughly going to be resisted by this one. So that is the shear. Now in terms of the tension and compression, exactly like designing a steel hollow section or designing a concrete beam, you will have your stress something that looks like this. You have a peak compression that is in this flange, peak tension in this flange, and you're gonna have a peak compression at the other flange at the bottom. So basically you've got these two returns resisting the shear, and the front and the back flanges are resisting the flexural compression and tension stresses. So now that we are on board with this, let's start to look at how we can calculate the forces in the flanges and how we can design the shear forces to be transferred in between through a composite action. Alright, so the first thing that we want to calculate the stress, it's the very famous formula that we all have seen in our solid mechanics. Sigma, which is the stress, is equal to my on I, or it's also equal to m on z, where z is basically I on y. So it's this is z, and then it is I on y. In this equation, we know what is our m. We can calculate our I from the core, and we can calculate our y. So let's look at how we can calculate that. In calculating the y for just simple calculation by hand, you can assume it's a big solid section, the length of which is 3.3 meter plus this was a dimension that is to the center and center, so you need to add half of 180 on either side. So you add a full 180 to get the external dimension that is from here to here. So this is going to be 3,300 plus 180, which gives me 3.48 meter. In the other direction, it's exactly the same, 2.7 plus 0.18, which is going to give me 2.88 meter. That is, and then you can calculate your I value of these two. If you're bending in this direction, let's call this our x-axis. So this is my I-XX, which is about the x-axis. So my I-XX of a solid rectangle, like I'm sure all of you have done in structural mechanics at some point, is BD cube on 12. In this case, my B is the 3.5 approximately, and my D is the 2.88 to the power of 3 divided by 12. Let's work it out using millimeters just for consistency later on. So that gives me a 6.927 times 10 to the 12 millimeter to the power of 4. So that is my I of the big box. Now if I want to work out my I of the internal box, again in this case it's gonna be 3.3 minus 0.18, which is gonna give me 3,120, and in the other axis it's also the same, 2,700 minus 180, which gives me 2,520 millimeter. Again, I can work out what is my IXX, and let's call this one, this was the outer IXX and this was the inner IXX, which is again 3120 times by 2520 to the power of 3 divided by 12, which gives me 4.16 times 10 to the 12 millimeter to the power of 4. Now what I need to do is I need to subtract my inner eye from my bigger eye. So effectively I'm having all of this and then I'm subtracting the inner eye out of it. So I'm left with eye of this 180 thick core. So that gives me 6.927 minus my 4.16 times 10 to the 12 millimeter to the power of 4. That is 2.767 times 10 to the 12 millimeter to the power of 4. So now I've worked out what is my eye of the core about the x-axis, which is resisting my Vy and my My. Now that I know what is my I value, Y is the centroid to the furthest point in the section, which is this one, and we can take that to be 2.7 divided by 2 plus 180 divided by 2. So my Y is equal to 2700 divided by 2 plus 180 divided by 2, which gives me 1440 millimeter. And that, using the I and the Y, I can work out what is my Z, also known as the elastic modulus, and that is equal to I on Y, so that is 2.767 times 10 to the 12 divided by my 1440, which gives me 1.92 times 10 to the 9 millimeter to the power of 3 now. So now I've got my Z about the XX direction. I can repeat exactly the same process to calculate what is my I, Y, and Z about the other direction. But for this example, we're only going to be working with the Y direction just to simplify things. Now that we've got our I, Y, and we could calculate the Z, we can jump back to calculate what is our peak stress. So in this case, our peak stress in the XX direction is equal to M on Z, and our design moment in this direction was 4,500 kilonewton meter. So 4,500 kilonewton meter, then we multiplied times by 10 to the power of 6 to convert it to Newton millimeter pretty much. So we are using the same consistent units over here, and then we can divide by our Z, which gives us 2.343 Newton per millimeter square, or it's also the same unit as an MPa. So what we're getting here is a stress, and this stress is the stress in the flanges that we were talking about earlier over here. This is the peak stress that we have in the compression flange and the tension flange. By the way, if you're interested into going deeper into lateral loads analysis and design, as well as modeling a complete full building on the finite element analysis software called ETABS, you can check out the links in the description of the video below. There is a full course that I've prepared on Udemy, and you can access it with the link below for a heavily discounted price. And with this stress, we can design for our compression and tension forces pretty much. So with this 2.34 MPa, if you want to know how much is your tension force, for example, along the tension flange over here, what you need to do is you got to take your 2.34 MPa. This is a stress, so you multiply it by the section of the flange, which is 180 millimeter, and you can multiply it by 1000 if you want to know how much is the tension force per meter. So this is per meter. So when we calculate that, we are basically getting 421 kilonewton per meter, and this is positive or negative, so it can be our tension and it also can be our compression. So this is the tension and compression forces in the flanges due to my overturning moment. Now that's not the end of the story, because don't forget that this core is supporting some gravity load. So always remember to add your compression stress over here. So let's say, for example, it is supporting about 3000 kilonewton of compression load. And to convert this into equivalent stress, we basically got to work out what is the area of our concrete core. Again, it's the outer area minus the inner area. So if we can just divide straight away, if you remember, our outer area was 3.48 times 2.88 meters square minus my inner area, which was 3.12 multiplied by 2.52 millimeter square, and basically, sorry, this is a meter square actually, and that gives me how much is my compression stress, which works out to be 1.38 MPa. So this compression stress is compressing the core uniformly, so it's acting pretty much across the whole core, giving me a uniform compression of 1.38 MPa. So at the end of the day, my stress is going to end up looking with less tension and more compression because of my axial load. So my peak compression over here is what we calculated previously from flexural stress, which was 2.34 MPa, plus my 1.38 MPa from the axial load, and this basically gives me 3.72 MPa in compression. Now in tension, I've got negative 2.34 MPa because it was a flexural tension, but I've got the compression stress from my axial load that closes a little bit of this tension, so it works out to be only minus 0.96 MPa. So now this is my net tension and this is my net compression that I'm gonna design for. And it is important to consider your compression because, as you can see, it actually helps you to reduce the tension, which you are using the steel reinforcement to resist, and it helps you to actually check for the realistic compression stress at the flanges, which you might be overlooking. Now that I've got my 0.96 MPa, I can work out my final tension forces, which is times by 180 millimeter times by a meter long, which works out to be 173 kilonewton per meter. And based on this force, I can work out how much reinforcement I need. So with safety factors multiplied by your area of steel that you need times by the steel grade, that basically needs to be the 173 kilonewton. And here in Australia, we are using grade 500 reinforcement. So we can straight away use our safety factor of 0.85 times by our steel grade of 500 MPa, and that is going to give me 407 millimeters square per meter. So with this sort of reinforcement, we know that because it's undergoing in tension and to the concrete code, we will need to actually provide 2 layers of reinforcement. So we can go ahead and divide by 2 to know how much reinforcement we need to put in each layer, which gives me about 203 millimeters square per meter, which is actually quite small, and I can go with a minimum bar spacing. Let's say the minimum N grade bars that you can use. If you're not sure, you need to use N bars in the lateral load resisting systems. So the smallest N bar you can get is N12s, and the maximum spacing is basically 350 millimeter centers. That will give me about 322 millimeters square per meter each face, and if I have times 2, that would get me back to the enough tension I need. So there we go, we've designed the tension force at the flanges, and we are assuming it's reversible. So this 4500 can be going downward this way, or it can be going upward this way, assuming it's earthquake or wind, and it's fully reversible load case. So we'll need to put this reinforcement in the top flange and the bottom flange. Now we need to check our compression design. With basically this 3.72 MPa, we can work out our wall compression capacity using the wall design equation from the code, but you have to be careful for the restrictions, such that you need to provide 2 layers of mesh, and the soil classification cannot be class D or class E. Otherwise, you will need to actually design for this stress. You'll need to convert it to a force. So 3.72 MPa times by the 180 times by just a meter long section, and that would basically give you 670 kilonewton. And with this load, this is already ultimate load, you can design 1 meter section of your core wall as a column, except that you are not gonna be adding in the legs unless you need to add in the legs for other reasons, like using a higher concrete grade. So this is fairly straightforward. You can use any design equation for a column or for a wall to check for the compression stress, and we know how to work out the tension reinforcement in the flanges. Now we've done the design only in the Y direction. I'll leave it to you to work out how much is going to be needed for the other direction, which is the MX, and I'm going to put the answer in the video description just to check if you got this right. In the next lecture, we're going to be actually looking at the shear force design through the walls, and how we can check the shear interface here if we're using precast concrete and we want to join our core walls with cast-in plates or weld joints. As always, if you find this lecture helpful, please give me a thumbs up, subscribe to the channel for future videos, and share it with someone who can benefit from this. Stay awesome, and see you in the next lecture.